Hello, everyone. My name is Nathan, otherwise known as Old Man Builds. We got Benny Factor here, and we have Michael from England as well. How you doing, everyone?
Hi, good, thanks.
We're,
Hello.
we're going to be talking some more Rodin Coil tonight, and Michael's going to tell us some stuff and show us what's going on.
Right on. Ben, do you have the demo paper that I emailed you?
I'm sorry, which paper?
I sent you an email with my presentation. It's got a couple of images of my device that are replicated. It's the Tesla magnifying transmitter.
I do have that. That was sent. What was that sent yesterday or a couple days ago?
A couple of days ago, yeah. I think during the meantime, I'm just going to read an introduction from Professor Konstantin Mill. Basically, my replication attempt is based on his information from this book here. It's called Scalar Wave Technology. So Professor Mill had done intensive research, and I wanted to replicate the Tesla magnifying transmitter. And I did the replication, and I wanted to read a little intro from this book, and hopefully you'll be able to hear me. I'm just going to read this introduction here. Yeah, that's right, yeah. So this is just a preface of the book. It says, when there is talk of free energy, when efficiencies are greater than 100% are promised, or even when inventors emerge with perfect blueprint for a perpetual motion machine, any doubts are justified. All too often, faulty power measurements misled, or an energy source is being drawn unnoticed. Responsible scientists, therefore, accept such statements only after carrying out their own tests to establish whether they can always reproduce the measurement with the instrument familiar to them. All skeptics can and should reproduce my experiments. This is from the book. They should not learn about results in the media, but they should gain their own experience of electric scalar wave transmission themselves. 100 years ago, Nikola Tesla performed the same experiment, but with very high voltages and controlled spark gaps. Because even at that time, more energy arrived at the receiver than the transmitter had sent. Tesla described the transmission station as a magnifying transmitter or a boosting transmitter. Unfortunately, his Colorado Springs was too complex and expensive for any university to be able to afford it. Consequently, the results remain unconfirmed. No scientist in the world has the right to challenge the results obtained by Nikola Tesla unless he repeats the experiment on a one-to-one basis and can provide appropriate proof of his findings. That has not been done up to now. And then the professor talks in depth about all sorts of experiments and information related to Nikola Tesla's TMT, the magnifying Tesla magnifying transmitter. So I call it TNT because it's easier to pronounce. So just a little bit of intro about me. So just as on the document here on the screen, I was interested in John Bedini's electronics. In fact, he got me interested in electronics because, I heard the word energizer, pulse motor. I was really excited about it. And I started very small, the small edge SG motor, the schoolgirl motor, just the one transistor. Pulsing motor, really excited about it. And then I did the SSG, which is a more advanced version. Although it's called Simplified Schoolgirls, it's actually a more advanced version than the SG one. And then I just got more and more interested about electricity and radiant energy, really. So I wanted to talk about this technology, this scalar wave technology, which comes from the Tesla magnifying transmitter. And so I tried a replication, because just like in the book it says, do not believe a word of really what people say, but do your own experiments and figure out if it's true or false. And it's healthy. It's good to be skeptics or skeptical about things, and that's what I did. I tried to replicate the experiment. Now back then, Professor Mill was selling kits, but the kits were really, really expensive. So I built my own version of the TMT. Ben, can you scroll down a little bit? We'll just have a look at some of the images. Yeah. So this is the devices. So there's a transmitter, which is the one at the front, which has the little aluminum electrode, and there are two aluminum half spheres baking trays, which I had to sand down to remove the insulation. And I drilled through the top, drilled through the bottom, and put a bolt to tie them up. And then the sphere rests on a stick, just a wooden stick, wooden dowel, 6 mm wooden dowel. And then we've got a transmitter and we've got a receiver. And so the setup is not so difficult to do, but it's very difficult to tune the system. It's very, very difficult to tune the system, and I think that's why so many replication has failed, out there, because it's really best, if anyone wants to try to replicate this experiment, that they grab Professor Mill's book. So there's two books that I'll show down in the bottom. This is the photo of them, but essentially one of them is the explanation of how to set up everything. And then there's tests to figure out if you have it, if you have the scale energy or if you don't. So it's very complicated, and I'm not a physicist or an electrical engineer, but my understanding on the device is basically there's two kind of waves that I understand. There's the standard Hertzian wave, which is like a radio wave, if you like, and you have a magnetic fall off, which means that you have your radio station and your receivers, and the magnetic waves falls off away from the station. But as the distance increases, as the distance is greater, the magnetic fall off, or the energy, is less, right? So what happens is they have to pump a lot of power in the transmitters for the receivers to receive anything, and that's the Hertzian wave. But this device that you see on the screen here is not a Hertzian wave, it's a scalar wave. And Professor Mill was at the Tesla Tech conference in 2007, and he actually did a magic setup where the transmitter was up in the corner of the room, and the receiver was a little aluminum ball on top of a little boat. So the boat was the receiver, and the boat motor would actually spin in the water on its own, right? But because the water was earth grounded to the ground, and the ground connection is how the devices could stay attuned, right, in resonance. We'll always hear Nathan talking about resonance. Yes, we need resonance. It's really important. It is really important, resonance. And in the book, in the scalar wave technology, because we use very low power, because it's actually difficult to set it up. We use low power, so Professor Mill just used a cable to represent Earth ground, but Nikola Tesla used actual rod planted in the Earth ground to transfer the energy from the transmitter to the receiver. And I've got a photo which is kind of cool in the book. Just 1 second. I'll just find it here. Yeah, so this is the transmitter. This is the actual Tesla magnifying transmitter, and it looked nothing like we see on the internet. It's a tiny little pole and a small ball at the top. It's quite underwhelming, but this is actually incredible, this technology. And to show you that changing materials changes everything. So for example, you can see on the photo, I've got this aluminum sphere at the top, which is my transmitter, right? And we've got the receiver on the other side, also has an aluminum sphere, both the same size. The transmitter is a half wavelength, and you can see the pole of the transmitter is half the height of the receiver. The receiver has a taller antenna, but also the receiver also has a full wavelength. So the transmitter is wound clockwise and the receiver is wound counterclockwise. So they're out of phase with each other. So what I wanted to, the point of the story was, if you change material, for example, I had, this is a copper ball, right, with a stainless steel rod. Those balls are industrial toilet flush lever, if you can believe this. It's absolutely enormous, right? I tried the exact same experiment that you see in the photo with copper balls, and guess what? It didn't work. So I don't know if it's the copper ball or if it's the stainless steel rod, but again, it's best to pick up the book if you're interested to learn more about it. But this is my experiment, so I'll talk a bit more about it. Ben, if you can scroll down a little bit, please. Okay, yeah, so those are the two books. If anyone's interested in what I'm talking about, it's absolutely a fascinating subject. Not just for technology, but the benefits that everybody could maybe in the future have, maybe, in the near future, hopefully. We don't really know, but just at least for your curiosity and for learning a bit more, I recommend those two books. Those the books that I've got. So I've got the Scalar Waves book. So this one covers a range of devices, not just scalar wave, but really, really, really interesting books, because Professor Mill talks about other devices, but you won't see them on the internet. They just don't exist on the internet. So I really recommend this book. I don't get any money from talking about those books, by the way. I'm not related or affiliated in any way with Professor Mill. And this book here is more of a technical book. Really, this book is also, Professor Mill sells some kits, but I couldn't afford them, so I did as close of a replication as I could. Ben, can you please scroll down a little bit? So there's the, I'll just talk about that, yeah. So we can, next page, please. Onto the experiment. So we've got 2 pancake coils, and I don't know if you can see, I've got one right behind me here. I don't know if I can, I'm gonna try to move my webcam just to show you a little bit. This is really ad hoc, guys. So I'm gonna try to move this if I can. I've not tried it before, so yeah, okay. So, right. I don't know if you can see the LED light right here. Ben, can you see the light? Yeah. So those are the LED lights. Now, this is the receiver. You can see it's really tall, and it's got 2 little LED lights. Here we're not we're only just trying to demonstrate a sort of proof of concept. And you can see there's a red cable here. They're right here, there's a red cable. This is my sort of earth connection going up at the end of the room, which is down there. So the transmitter is down there. And now going back onto the device, there's a test we can do to see if it's a Hertzian wave or a scalar wave. So I'm going to just grab this mesh. So this mesh here is, we've got chicken wire, and we've got a mesh, a finer mesh on top, because it stops different radio waves. So we've got a really, really fine mesh, which is a copper mesh, copper coated and still inside, and then we've got a chicken mesh. And so if I put this mesh behind the receiver, the light should dim if it's a Hertzian wave, okay? So here's the exciting moment. Ready? So here we go. So you can see nothing is happening. So it's really, really exciting. I don't know if people can see this, but this is a really exciting moment, because it shows that it's not a standard Hertzian wave, but it's a scalar wave. I'll just try to move the camera back now. Right. Just move it back in place. And I'll just talk a little bit about the experiment that I've done. Ben, could you please go back to the document? Yeah, so 2 pancake coils, one clockwise, which is transmitter, and we've got away from the picture is the receiver, which is the counterclockwise, which is this one. This is the receiver here, and it's I'll tell you the way I calculated, because basically the coil can't just be wound like it has it's like an antenna. So I had to go on a dipole website and calculate the wavelength, and the wavelength tells me then the coil, the length of the coil. So the issue with the wavelength is that it's based on the speed of light. But here we're not doing the speed of light. We are doing 1.5 c. So we're doing 1.5 times the speed of light. So the reason why, it's because the waves of the scalar wave travels faster, and the scalar wave is completely different from the Hertzian wave, because the Hertzian wave, as I was trying to explain, there's a magnetic fall off. But the scalar wave, it's almost like a beam, and it goes from point A to point B, almost like a line. And obviously, it's a very layman explanation, because I'm not a scientific. So I hope you'll forgive me for that. So I've explained the little baking trays, it makes me laugh because they're baking trays. I think you can cook like cookies and cakes and apple pies. I'm not sure, but anyway, so Ben, can you please scroll down a little bit? We'll just carry on with the thing. Yeah, so okay, you see the lights here, you see I've put the mesh. Clearly it's not a Hertzian wave because the Faraday mesh does not block the signals, right? But you'll think, well, yeah, maybe. So I wanted to take some more photos and show you my process. So Ben, if you could please scroll down a little bit. Yeah, so this is my setup. So what I did is in the book, Professor Mill explains that the way to find resonance is you put them closer first, because it's a lot easier to tune it, and it's very complex to tune it. I mean, it took me a whole day just to actually tune it. The first time I did it. The second time was more like a half a day because I had lost some of the capacitors and the resistors, and there's matching impedance. It gets quite complex. So here in this image, Ben, if you could scroll down a little bit, please. So in this image, I'm just showing that the transmitter is only less than 10 inches away. From the receiver, and then you can see the LED lights. So this is what's really interesting. The LED lights are really dimly lit. Yes, yeah. So you can see here, it's really, really dimly lit, okay, and not really close to each other. So if it's a Hertzian wave, as you move the receiver away from the transmitter, if it's a real Hertzian wave, the light will dim off. So meaning the magnetic fall off, based on the law of the square, will fall off. So the more you move your device away from the transmitter, the less power you receive, right? So this is a normal Hertzian wave. It's a magnetic wave. This has got a complex name. In the book, it's called longitudinal transverse wave. It's a magnetic longitudinal transverse wave. So it's a different type of wave. Ben, could you please scroll down a little bit? We'll show the progress. So here, this is what I'm talking about, the law of squares theorem, and it's the square of the distance. That's all really the takeaway from this is the square of the distance. So, like a normal Tesla coil, when we put the little halogen bulb next to it, it lights up really brightly, and it's really exciting. But as we move it away, there's a magnetic fall off, and this is based on the law of the square. The law of the squares, or law of squares. So this is just a little clip from Wikipedia just to explain it, because all I understand really is the further you move it away, the less power you get. But in the experiment, this is the opposite. But it's the opposite to some extent, and that's what we're going to talk about. So I move this time the receiver, which is 10 inches close to the transmitter, and I move it 2 meters away. And so according to Hertzian wave, the light should be dimmer as you move it away, okay? So Ben, could you please scroll down a little bit? Okay, so here it is. I moved it, I think it's 2 meters. We can see the light. It's still lit up. So, which is very interesting because it's 2 meters away and it's still lit up. And in fact, is it the same brightness or slightly brighter? Well, I'm going to take a closer picture of this. So Ben, if you could please scroll down a little bit. Okay. Oh, there they are. So this is really exciting because we can see that the LED are brighter. They're clearly bright. I mean, there's no power measurements because I honestly wouldn't be able to measure the power because it's very, very high frequency. So I'm not an electrical engineer or a physicist. I don't really know anything about those measurements, especially they are in megahertz. So the transmitter is transmitting at 6.67 megahertz. So there are ways to measure it, but my measurements will be probably all inaccurate. So here I'm really just talking about the subject matter, which is scalar wave, and Tesla magnifying transmitter, which is, to be fair, it's absolutely magical. Ben, can you please scroll down a little bit? Right, so Professor Mill called this energy radiation energy. And so something strange happens when I put my hand in front of the transmitter, so about maybe 2 inches away from the transmitter, which is on the other side of the room behind the glass and the wall. It's way at the back. When I put my hand in front of it, it sort of tingles a little bit. And it's a very strange feeling. And when I turn off the function generator, I feel nothing. So this is a very strange thing. It's really is a different wave, and so here I'm saying it's a directional vortex spin, and I've got an image that I wanted to show you what Professor Mill described it, and I really admire Professor Mill of the work that he's done over his lifetime. Because without him, I would have never been able to replicate this experiment. So I'll try to show you a picture if I can. Okay, I can't find it, so that's no problem. Okay, here we go. So it's probably not the best picture in the book, but it's good enough. You can see those little spheres. They are the vortex spins, and they're directional. It has a direction, so it's not a magnetic fall-off as such. It's almost like a beam, if you like. Right. So yeah. So I think the issue around Tesla magnifying transmitter is, from what I understand, and I could be wrong, so please forgive me if I'm saying something wrong, but from what I understand, Nikola Tesla was an electrical engineer and not a physicist as such. And when Nikola Tesla discovered this very strange effect of the fact that this wave could go through walls, metals like Faraday mesh, wood, glass, he didn't really know what it was. He had discovered it, and the science had not actually even understood it until Professor Mill spent his lifetime researching it, got severe criticism for his work, and got recognized at the end for his amazing work. And it's only just now we're starting to understand how it works, and it's still early days, because there's so many people on the planet. It takes time to reach them. Ben, can you please scroll down a bit? Yeah. So this is what I'm using. Here I'm using 12 volt peak to peak, 6.67 megahertz. The amplifier, to be fair with you, still outputs 10 volt. I just measured up with my oscilloscope, but probably a lot of current is pumping out because it has to overcome impedance from the pancake, and also I don't know if I showed a really good photo of it, but the primary of the transmitter is extremely loosely coupled, so it's I mean, that's the way I was understood it. It has to be loosely coupled, so there's massive amount of losses, which defeats everything we sort of understand. But this is the way I set it up. So Ben, can you please click on the video just to show the setup really? Yeah, so this is just the function generator. The frequency is 6.67 megahertz. This is the small, tiny sine wave amplifier that I've got, absolutely tiny. This is the primary, the black wire is the loosely coupled primary. This red cable here is the connection, the earth-ground connection, if you like. Here we're about 4 meters away, or almost 5 meters away from the transmitter, and you can see the light is still bright. Thanks, Ben. Yeah. So this is it. Thank you, Ben. Awesome, thank you. So yeah, so here I've moved it 4.9 meters away, 15 feet, give or take, and the light remains bright. And I would even argue it's still a little bit brighter. So yeah, that's it. Next page, please, Ben. Yeah, so just a photo here. It's really, really far, and we can still see the LED lights lit up. Next page. So here I'm just showing, so this is the measurement. Just the further I move it away, and it's still lit up, and this is maybe even a little brighter, which is really interesting. And then next page, please, Ben. Okay, so here I'm going all out. Let's put it behind a concrete wall, behind 2 washing machines that have their own mesh inside. In the next room, so maybe 7 meters away now. Ben, can you please open the video if possible? Yeah, so same setup again, just showing, the loosely coupled wire. And then this is the earth connection, which is just a cable. It's a single wire. And we're going next door. There's the LED light. And we can see they're brighter than the beginning, right? And here I'm just showing the washing machines and the concrete wall behind. It's behind a concrete wall and 2 washing machines. And this is the cable. So yeah, so that was the experiment that I've done. I don't know if there's any more images, Ben, on the document. I don't know if it's the end of it, but I think this was really cool. Like, it's just behind a concrete wall, it's behind 2 washing machines, it's the next room, and it still is lit up bright. So that's the end of the talk. My hope is maybe I hope I have motivated some of you, and if not in the scalar wave technology or the Tesla magnifying transmitter, at least keep on experimenting, because we learn a lot, we become more astute, we make a better world by improving technology. And it's not just one person, it's a movement. And I think we're all on the same wavelength when we just want a better world. And I think this was just an experiment. It was really exciting, really hard work to do, not easy at all, but really exciting. So thank you for your time.
That was amazing. Oh, sorry. Little confusion there.
That was really good, man. I appreciate that.
Yeah, thank you. I got a couple of questions for you, if you don't mind. But I'm really impressed with your scalar wave technology. That's really fascinating and something that I've been curious about for a while. And, how did Tesla do it? And so many people, didn't. And that's that was my main question, is what do you think most people get wrong with this when they're trying to reproduce what Tesla did with the wireless energy transmission?
So I'm not any more intelligent than the next person, but the thing that led me to the success of this experiment is this book. So if people try to replicate this experiment, they need the book. And I don't get any commission. I don't get any monetization from the book. It's just those 2 books. This one is a gold mine. You won't find any of that information on the internet. And this is from Professor Konstantin Mill. There's the link in the document to his website if anybody's interested. It's Professor Konstantin Mill, MEYL. And I think the main thing that people get wrong is the speed of light. So they do all their measurements, the antenna, wavelength, and everything, and they do, I think it's 300,000 kilometers per second. Correct me if I'm wrong. But what you do is you multiply that by 1.5. It's 450,000 kilometers per second, or per meters. I'm sorry, I don't remember. Sorry about that.
Right.
But this is the real. And so what happens is in the book it explains the tuning. There's loads of things to tune. So the first time we tune it, we get first resonance, which is around 4-ish megahertz. The light comes on really bright. So we've got the receiver that has bright LED lights. We're like, okay, great, this is it. And then you put your hand in front of the transmitter, and the light goes off on the other side. And you're like, nah, this is wrong. This is a Hertzian wave, right? The light goes off. So, and then you multiply that resonance you just got by 1.5. And so I was around 4.9 megahertz or something like that. And I go up to 6.67, which is roughly 1.5 times this resonant frequency. And then suddenly I get the lights, but they're not very bright. It's like, well, what's going on? This setup is awful, right? Put my hand in front of it. The light does not move. The light does not dim. Wow. The light does not go brighter. It stays. The receiver stays the same. I think that's the real thing is those two LEDs. They are wired positive in parallel. So one is positive and the negative together, and the other side of the two LEDs is positive and negative. So the polarity is almost like AC polarities. So we need to check that the two LEDs are lit up. If we only have one LED light up, it means we've only got one cycle of the sine wave. We need both LEDs. So the second time and that's the real trick that helped me work it out, because there's so much to. It's really difficult. There's impedance matching. So when your little frequency generator and your amplifiers push that stuff, that electricity, that power through the primary, there's a function generator has an impedance of 50 ohms. And then the receiver also needs a matching impedance to it. And then you need to add some capacitance. So it gets really tricky. Honestly, it's not an easy replication, and without this book, not possible. Because what I'm saying here is I'm giving you some information, but not all information, because, like I said, Professor Mill wrote a whole book on this. So I'm just giving some information. But to answer your question, Ben, what people get wrong is the 1.5C, and what's interesting with this scalar wave technology is that they are this vortex spin I was talking about. But in the book, Professor Mill says that there's more to it. He talks about neutrinos, and Professor Mill believed that neutrinos come from a black hole. They come out of a black hole, which is okay. So and neutrinos come out. So we thought everything comes in the black hole and nothing comes out. No, according to Professor Mill, there's little neutrinos, and they are massless. They are massless particle of energies, and they can't have any mass because they're fighting the black hole. They're fighting to come out. And my analogy, which is a really bad analogy, is when you pour a glass of water and you have this boop coming out, right? And it's not scientific, right? But this neutrinos flies into the scalar wave signal and amplifies it. So what Professor Mill is saying is that those neutrinos travels everything. It goes through everything. Goes through matter. Goes through earth. Goes through the grass. So we don't know if do those neutrinos actually help the grass to grow. I'm not a professional, but those are questions I'm asking myself. But anyway, so the scalar wave transmitter catch those neutrinos, according to Professor Mill. I don't know anything, So, but apparently they catch the neutrinos, and that's how the signal slightly gets amplified. And there's this story, which, again, don't quote me because this is what I heard. It could be completely wrong, but when Nikola Tesla transferred his power on the other side, like miles away, on the side of a mountain, there was lots of lights, and the whole wall was lit up with lights. And when he went there, it was like, there's something wrong. There's more power received than I was transmitting it. And so that's the scalar wave technology. It grabs some neutrinos along the way. I don't know if, you'll have to read the book to understand if there are any over unity effects. In the book, some of the students' replication believe there's at least 5 times over unity effect, but that was on milliwatt. Okay, so, and they are students of, physics students, electrical engineering students, and they are like little advocate of Professor Mill, because he's an absolute genius, an incredible man, absolutely incredible. And if you search Professor Mill on YouTube, there's stuff that it doesn't say much on the internet, because a lot of people have different opinions. But in his books, it's his own opinion, and that's what I like. I like the fact that he puts his own opinion in the books. And there's stuff that I'm not going to be allowed to talk online, but there's stuff that is magical. That's what I'm going to say. Like magical, like in the real sense of magic. So, but obviously, I don't have the equipment or things like that to go that step further. But if you read stuff, you're like, what did I just read? This is not possible. But I'll just leave it like that. So
we get that reaction a lot from some of these devices when you start looking into them. Like, what that supposedly does what?
I was really impressed that you got it in the washroom and it was so far away, and you still got the same signal from it. That was really cool.
Yeah,
and really I like neat. The mesh as well. Sorry, Ben.
No, I was just saying. I was just agreeing. This is really neat.
And the mesh as well, the Faraday mesh. I mean, it's like what you put the Faraday mesh inside, like behind the receiver antenna, and it's still fine. So yeah.
So, just describe the one where you put your hand in front of it the first time. You were in the wrong radio signal or wrong wavelength. What was it again?
Yeah, so the first time I put my hand in front of the transmitter, the little antenna ball or electrode, right. the aluminum ball, when I put my hand in front of it the first time, and I was at 4.8 megahertz, as soon as I put it in front, the receiver light just cut off. That was it. There was no more. And this is like a Hertzian wave, so the signal gets blocked literally with the hand, and just my hand, because we're talking, yes, the signal's been amplified and all that, but I'm using my hand, and the light goes off. And as I move the device away, you would expect the light to dim more and more and more and more, so you get a magnetic Hertzian fall off. But when I change the signal to 1.5 the speed of light, I put my hand in front, and the light remains the same consistently. And I move the light, the receiver away from my transmitter, move it away, and the light gets brighter. And I move it more away, it gets a little bit brighter. It's not gonna like blow up or anything. It just gets a little bit brighter to where it's fully lit. And then I move it behind the concrete wall, behind the washing machines. Okay, come on, it's got to stop. But it's not. And the very strange thing is when I put my hand in front of it, now I wouldn't put my body in front of it. I wouldn't, I don't know, so, but it's just my hand. I've just put my hand in front of the electrode, and I felt this tingling sensation. Very strange. I can't even describe it because it's I've never had this sensation before, so it's very hard to describe. It's a little bit of tingling, but you feel it like through your nervous system, through your brain, through and if you get those books, honestly, it's a treat. It really is a treat, because there's stuff that I'm not talking about, which are in those books. And my hair was like going up down my back, because it's just incredible, the stuff that, and Professor Mill, who is an absolute genius in my eyes, took it a step further. So if you imagine incredible effects of what we're seeing here, which is a true wireless transmission of energy with higher voltages, you could put a rod in your backyard, a rod to the earth rod to your neighbor, turn it on, and your neighbor has electricity hooked up to the earth ground in any room of the house. So we're talking no wire. In my experiment, yes, I have a wire because I'm stimulating the earth connection. I'm only using 10 volt, guys. So, we're not talking high voltage here. So 10 volt is not gonna go through miles away through the ground. You need higher voltages than that.
So I have another question for you. Is it more like static electricity when you feel it around you? Or does it feel like a penetrating electricity? Because you said it goes through, but does it tingle on the outside, or does it feel like both?
It's totally penetrating. Totally penetrating.
More like a microwave.
No, because microwave, you wouldn't feel it. So if you're in front of your microwave, so the way we discovered microwaves is sailors used to be called, and they used to, when they dock at their naval station or wherever they were really called, the sailors, and so they used to sit right in front of the big, massive antenna transmitters. They used to sit right next to it because they were warm, right? They were warm, and so they always used to gather there and keep warm. Let's just sit next to the antenna. It keeps you warm. And then years later, they all died of cancer. And what's happening is they were cooking from the inside. So microwaves cooks molecules. It cooks, it shakes it and cooks it. But here it's scalar wave. It's very different.
Sorry, I'm just trying to pin down everything so everybody understands, you know what I mean? What things are. So
That's so cool.
Yeah. It's like it bounces around the whole room and then hits everywhere.
So there's a photo I wanted to show you, and I hope next time you see this photo, you'll think, I know what this is. And this is a photo of Nikola Tesla, if I can find him. Did I lose the page already? So, yeah. This photo is Nikola Tesla, the famous photo of Nikola Tesla holding a light bulb.
Yeah, I see that one.
This one here.
Yes.
Yeah, that's iconic. I love that.
It's
photo.
iconic. But this wasn't a tall Tesla coil like we see, and he didn't have a tall Tesla coil right next to him, or even a couple of meters away. This was radiation energy, which is scalar wave energy, because apparently there's like really strange stuff with this stuff. When you put your finger towards the light, you feel like it's pushing your finger away from the light. There's really strange stuff like that. But this image is the real Tesla magnifying transmitter.
Hold on.
Wow.
You say when you push your finger next to the light, does it feel like a little field bubble around it when it pushes back, or what are you describing there?
No, so this is what I read in the book is there's the light bulb, which I don't have one here, but apparently which I don't have all the equipment and stuff, but apparently when the finger goes next to the light bulb, there's a sensation that is actually pushing the finger away from the light bulb. And I don't know why, I can't explain why, but it's related to scalar wave energy. So and stuff, as he's holding the light bulb here, he's actually earthing the the light bulb. So he's got a connection, if you like, and it looks like magic, but it's not the normal. It's not the normal Tesla coil, which is. See, this is not the normal Tesla coil, which is like. Don't know if I can. Well, it's not working. But yeah, it's not the normal Tesla coil that you get with the light coming on. I think my batteries are flat. Maybe. Oh, here we go. Don't know if you can see it. It's just dimly lit here. The battery are flat. You can see it. Yeah.
I see it.
Yeah. So it's nothing. It's nothing to do with this. This is a different technology. But it's still a lot of fun this anyway, so I like it. But it's different. It's different technology, guys.
And
Well,
you did.
Go ahead.
Oh, I'm sorry. Go ahead.
No, go ahead.
Oh, I was gonna say you mentioned the law of squares, which I was really excited when you mentioned that. That's something that John Searle mentions in his work. And I was wondering, like, where did you? Is that's in the book too? Is that something you got from the book, or is that something you borrowed from like John Searle?
It's correct. It's from the book. So the book says there's an interesting effect that you will get when you tune into this wave, is that it will break the law of squares. So the law of squares is not applicable anymore because it's a different type of spin. So it's not all the laws applies, but I think there's just different versions of laws. So for example, the law of thermodynamics or law of squares, there's clusters of people around the planet. They have their own versions of law of thermodynamics. It's like the revised edition, if you like, So for the layman like me, I only know the first law of thermodynamics, but perhaps people a bit more astute than me may have a different version, a revised version, law of thermodynamics version 2.0. So, and there's clusters of people who knows different things. And I think the stream that Ben and Nathan are doing, it's incredible because I learn so much, and I get motivated from Ben, I get motivated from Nathan, I get motivated from all the hosts they have, and thank you guys for having me, because it's been a blast to show you this. I thought it's so exciting, but some people might say, no, it's boring, and that's fine. But as long as I can, as long as they carry on experimenting, I think that's my happiness,
No, this is great. This is cutting edge
really
stuff
good.
that you're doing.
We're building some UFO stuff, so you're not going to do it without this kind of a wave. So just so you know, we're changing how we change everything. Yeah.
And you put this in the field, bit of aluminium around, it'll probably take off, right? Well, where's my coil? It's gone. And there's like a UFO there. It's like, hey, dude, stop throwing stuff at me, okay? I'm just sleeping up there, right? Just leave me alone. This guy, really,
Hey, you see the T-shirt I got on just for today? It's my Rodin, my VBM T-shirt.
Right on.
Available
More
at my
appropriate than the
shop.
ones we usually get on.
Yeah. Hey, it's Gerald.
Oh, we got to have Gerald come in. Hey, Gerald. Nice
Hi,
to see you,
Gerald.
buddy.
Hey everybody, how's it going?
Good.
Right,
Good.
good.
Good. Glad to be
Sorry
here.
I'm late. Good job on your coil, Michael. I've just been catching up. I got in late, but dang.
Yeah, and it's got the coil in the inside, the pickup coil in the inside.
So this
A
is
lot of
the
hard
90-degree coil, Gerald, just a 90-degree coil inside the frame. So inside the magnetic field, because it's like the eye of the storm, right, in the center, and then inside is stuff are happening. So I'm hoping that this 90-degree coil. So this is one thing I wanted to talk about is the 90-degree coil. So the bifilar coil inside. this is how I'm going to wind it, it's called a Mobius wind. And this is, sorry guys.
Oh yeah. Look, yeah.
So I don't know. Let me just try.
I know exactly what you're talking about. That's
So,
the
We can
Mobius
see it,
strip.
yeah.
Mobius strip. That's right. So this is from the. I don't know if he's a scientist or mathematician. This person, and then this is the actual wiring diagram of the Mobius.
Yeah, they modeled one of the stellarators on the Mobius strip and the way that it flows. They believe that that's the actual flow of time. They're not quite right, but interesting.
You said they
stuff.
modeled
I know
what?
exactly what you're talking about.
You said they modeled a what, Gerald?
Sorry?
You said they modeled that after a what?
The stellarator, it's like kind of like a plasma accelerator. That I'm not exactly sure if it's at MIT or if it's the Chinese version. I've been doing some research, so I'm getting it a little mixed up. I'll get back to you on the clarity of that, or somebody in the chat could correct me. But it's called the stellarator, and the Mobius strip is the whole machine is based on it. So it's interesting. I don't know exactly what they're trying to prove with the whole system, but I've been doing some reading recently. So that's go for it. Is that what's going on the inside of the Rodin coil? Is that
Exactly. So when we were talking to Ben and Nathan, and those guys are just incredible. I'm just so happy to be here, and thank you for having me. But when we were talking about it, Nathan had some amazing ideas, and Ben's got some amazing ideas, and Nathan's doing this coil, right, where you've got like a smaller coil inside the bigger one, which is genius, right? Absolute genius. Ben is doing some incredible stuff. Like, honestly, I'm mind blown with your experiment, Ben. And then, so that's why I'm trying to try something different. I'm still trying to stick to those amazing people, Erica and Danielle Nunez. I'm still trying to stick to their design, their, the shape, the big rings that they've got. So I'm trying to stick closely to what they've done, because if at least I can try to replicate, some of their effects, then I'll be really happy. And I thought, I'll try something new. So I've done this, and this is what Professor Mill. I'm just going to read one sentence about the Mobius strip. He says, the result is a strip which has neither top side nor underside, and neither right nor left border. And so what's happening is the electricity with the collapsing magnetic field must be doing something in there. I've got a friend who did some experiments, but unfortunately there's a really high frequency. So from what I understand, the PoE coil, in respect for Daniel and Erica Nunez, that they call the PoE coil, but also we call it the Rodin coil because I think it all stems from this amazing man.
Danielle Nunez, and it's from the Rodin coil.
Yeah,
I don't quite have the same aspirations for Marco Rodin, but I mean, hey, I'm not here to discourage. I love the fact that you're experimenting and trying new things. Man, I don't care what you're trying. The fact that you're doing it,
and you're on the right.
That's awesome. You know what I mean?
You're on the right track, sticking to the First Stop Energies, and basing it off of them, because they did 10 years of this trial and error. We should listen to that and see what they have to say about it and take it seriously.
Yeah, you can't discount their work by any means.
Mm-hmm.
Hey, Michael,
I wouldn't.
You show the front of the book again?
Oh, okay. Yeah.
Sorry, Taryn wanted to see the front of the book. See what the book
you want me to put it up on the he has a screenshot of it on the. Oh, there we go.
So this book here is, honestly, it's absolutely incredible. The amount of devices from Shinichi Seke to some amazing people, and this stuff you will not find it anywhere. Honestly, it's a gold mine. This is, in my eyes, this is one of the most important for research and opening mind. And this is written from, Professor Konstantin Mill. So this guy is the real deal. He's been researching those technologies for longer than I was born. He's absolutely incredible. And this is more on the scalar technology, so it's more like a technical. Without this book, impossible to even try to replicate this experiment, because it's difficult to gather information, and it's better to try it from the man himself. So yeah.
Did you get? I'm trying to get the windows right here. Right? No, there it is. Right. Did you get the books on Amazon, or is that something that you collected through time?
Those books?
Yeah. Yeah.
So those books, you can only find them in one place. You need to go on meyl.de. So it's MEYL.de. So I'm just gonna make sure MEYL.de. Have a quick look here. No, I'm so sorry. This is wrong. It's the wrong website. This is an art website, so let me just try again. Ben, can you pull up the website address from the document?
Is it MEYL.eu?
That's the one, thank you. MEYL.eu for Europe. So MEYL.eu, and you want to have a copy of those, at least the yellow book. It's honestly, the stuff that he writes into this book. It sends shivers down my spine when I read the stuff.
I love that.
If you like magic, have a read to that book. Honestly, they're a bit pricey, but it's.
I don't believe in magic. I just believe that magic was misunderstood science by the masses, but only understood by the few. So magic's a form of trickery, right? But really, I think it was just true science, just kept hidden. Like you, I like finding old books too, right? And this one's a little different. It's not quite a scalar book, but I love the fact that you're sharing that. If they'll allow me to order it, I'm gonna order a set of what you have there. That's awesome. Thank you.
Can you spell that book again, Gerald?
It's called Order Out of Chaos by Ila Pergogini and Isabel Steingers. I'm sorry if I butchered that name. I don't know if you can see that. My lighting sucks. There we go.
You got it.
Okay.
I got that on Amazon used, and it's in great shape. So,
and then real quick before we go on, Michael, is this the website you were looking at?
Yes, yeah. Apologies for the spelling earlier. I got carried away, but yeah, it's this one. It's MEYL.eu. If you click on your country and then you click on the shop, there's two versions. There's a German version. Professor Mill is from Germany, and there's an English version. So those books I've purchased are in English because I can't read German.
I can't either.
I just wanted to make sure I got it right so I could put it in the chat.
Thanks, Nathan. I appreciate it. I said the name of the website. Thank you very much. Yeah, thank you.
Man, we're going to be doing some more reading. You know how many books it takes to get to all of this technology?
Oh, yeah.
I mean, it's astronomical. The reading list that I've been given by everybody on YouTube is just, man. And they're not small books either. That's, 500 pages is the minimum usually.
That's a small one.
Yeah. Man.
Yeah, remember, I said it right at the beginning. We're not the first people to do this, and we probably won't be the last, but let's make a big splash when we do. Right?
Yeah. Gerald, every time you speak, you have words of wisdom.
There you go.
Where?
And you're funny as heck too.
So I did a video on waveforms and what you were describing with the Morbius strip on the part 2 of the waveform videos. You can see it in the waveform. You can see it's like it's twisting inside the waveform. You got to see it. It's pretty neat. Yeah.
You have it up on your page, Gerald?
Yeah, I just put it up a little while ago, actually.
I'd be interested to see what the field looks like under some magnetic paper.
You know what? I tried that, and this is why. Well, another one of the reasons why I believe I'm using scalar, 0 point, or ether, call it what you will. It doesn't show up with iron filings unless it's at very, very low frequency, like 7.83 or even at 2 hertz. But for some reason, the magnetic field doesn't appear on the paper like you would think it would.
So it doesn't interact with ferromagnetic materials at that range, or
no? It acts. It actually reacts with ferrite cores, and it does react with ferrite magnets. But for some reason, it doesn't show up on paper. I don't understand it.
Huh?
That's why
maybe
I'm thinking
something to do with the chemical process that's happening with the paper.
Maybe it's because of the way that the system's pulsed, and I'm capturing all the back EMF rather than it pulsing into the copper and creating heat with the back EMF and a way more magnetic field that shows the actual filings on paper. I'm not really sure.
I don't know how the paper works, but if it's based on heat, that makes sense.
I'm still trying to figure that one out because I've tried it a couple times and.
So that would mean like ferrofluid probably wouldn't do anything either, huh?
I've never tried it, so I couldn't say. It'd be an interesting experiment. I don't have any.
You're doing it on paper next to your coil?
Sorry?
You're doing it on paper next to your coil?
Yeah, actually what I did is I took the paper and I put it right on top of the coil and I was pulsing it. And I had iron filings and I put it on top and I didn't get nothing. I used aluminum filings, nothing. When I used a bunch of crushed rock from that rock I showed you guys, I got a little bit more than I did with the iron filings. I still don't understand the end of it, but who knows? Maybe it's a scalar interaction.
Try a thin piece of plastic instead. You may be interacting with the paper itself because of the structure of it. And the fact that you're using a lot of statics in your coil, it may be interacting with the paper as well.
Never thought of that.
Yeah.
That's interesting.
You're going to have to
I'm
a little bit.
My theory's been formed. I've been writing all day. I know my neck's going to be sore from it because I'm that old school guy with a darn pen. I hate typing, right? But I want to do my presentation like I'm hoping end of the week.
Maybe we've been waiting for months, Gerald. So
I know, but you know what? I hate to say it. There's this guy that I met, and he taught me something about temperature differentials, and my brain went, and I had to actually write it into the theory. Otherwise, it was missing a piece.
Sorry about that, Gerald.
I apologize for making everybody wait.
No, it's okay to be a little bit of a perfectionist. You want everything to be on point, you know.
I may not even be correct fully about the theory, but
you want your presentation to be right. You know, you want it to be the envision what you envision. So you know,
yeah, and I'm trying to snag little pieces of animation from other people's channels and send them messages saying, you know, I'm using it and I'm not representing it in your way, but I'm just using the animation, and I haven't gotten any no's yet. So yeah,
we're definitely excited. And when that day comes, it's going to be a massive event. Trust me. Well, we're going to have a lot of people watching.
Because of Nathan and you, Ben, and this group that's been forming, my channel is now at 817 subscribers.
There you go.
I noticed. Yeah, it's been climbing. So
it's climbing big, and I'm not doing enough to make it climb. You guys are helping me more than anything, so I appreciate that.
Yeah, this whole networking thing really helps, and that's what a lot of people do to help the growth of their page.
Well, the more experimenters we get together, and get working on their own projects, and everybody comes up with that other piece of the puzzle, the quicker we'll get this done.
And
The
that's
more angles, the better. I don't care if there's 100 guys with a different piece, you know?
I was talking with Nathan. We really think, Michael, if you're up for it, we'll help you create a YouTube channel.
Yeah,
So
You should.
I'm sure I'd like to see more of your stuff, you know, and I'm sure there's a lot of people here who would like to see more of your stuff. You got some interesting projects, and it's
absolutely.
kind of like it'd be a shame to like hide them in your closet, you know. Show us what you got if you like, you know.
But don't show your secret sauce if you're trying to keep it for
Right, exactly.
you know,
Yeah,
show
we're just
what
curious.
you
That's all.
have and how it works generally.
Yeah, whatever you're comfortable with, we're interested. That's all.
Yeah.
Thanks, guys. I think I'll definitely have a think about it. I think it's a good idea. I think you're right. I think all of you are right. I think what we're trying to do at the end of the day is just share information for research, and hopefully people are motivated enough to experiment. So yeah.
Yeah.
And these
Awesome.
workshops were helping. I mean, the podcast that Gerald and Nathan have on Wednesdays, and the workshop that I had on Sunday, you know, it's helping inspire people to actually do more building and actually, you know, experiment with this stuff.
Yeah, it helps when they have an easy place to start. That's the big thing. It's not like a big giant thing they're trying to get into. It's just simple engineering, and then they can get into the bigger stuff on their own.
I love the stuff. I love the workshop that Gerald and Nathan did the other day with the transistor and the Tesla coil. I thought that was absolutely amazing, and I think you know, if we have more people like you online, just just showing little things and motivating people to experiment, I think we're doing a good job. If people get motivated and experiment, and even if hopefully they don't believe a word we say, and hopefully they'll do the experiment themselves.
Exactly.
Because I've probably said a 1,000 things that were wrong, but this was my replication based on a book, and you know, and I hope I've maybe motivated one person, or at least they'll keep experimenting. So
yep, that's what it's all
for
about.
sure. Motivated me. That's for sure. Some of your experiments with the Rodin coil and the scalar waves, it's very inspirational.
And that's what we're meant to do, is inspire each other. You never know who's going to be the next Albert Einstein or the next, I don't know, name one of them.
Or the next Gerald.
Right? Well, I don't know. Yeah, that waveform that I was showing you, I don't quite it's a small oscilloscope. It only goes to 20 volts per division and down to, I think, 1 volt per division. So
Well, it would be good to get Michael's opinion on it in case it is a scalar wave. You know what I mean? Since he's dealt with them.
That's right. And you got the books to compare. So,
Let's take a look.
You want to put it up here? Or did you got it? Okay.
I got the first one, so let's play that.
Let's do it.
New coil footage.
Hey everyone, we'll try and do this video for my battery dies. All right.
Got to work on that volume, Gerald.
Vortex coil going on.
Yeah, I know.
Single pickup coil, 120 wraps on the ferrite core to a full wave bridge rectifier, then to this little meter. The primary of this coil is going to be pulsed with a modified Bedini circuit, and the secondary is going to go to this LED bank. We're going to pulse it with, I don't know if the camera's picking that up, 14.8 volts, give or take. And we're going to pulse it at 1,000 hertz, 1% duty cycle square wave, 20 volts per pulse. But the whole purpose of this video was to show you the waveform. So we're at 20 volts per division DC at 0.1 milliseconds. So we're going to turn it on in 3, 2, 1. And that's the waveform. We'll put a hold on it.
Wow.
And that's at 20 volts per division DC at 0.1 milliseconds. All right, we'll switch it up. go up a little. That's at 0.2. This thing's just ringing.
Holy crap.
All right, everybody, that's just a quick view. You have a great day.
Now you got to forgive me on my
Wow.
terminology if I get anything wrong, because I've just started learning how to use my oscilloscope, and
We'll put a
I'm watching learning videos about it. So
No, you're good. I'll be right in the same position when I get mine, Gerald. But I got a question for you because that looks like an H wave. Is that an H wave?
That looks like a ring right there.
A ring? Like what kind of waveform is
Oh,
that?
hold on, I just saw this yesterday. Hold on, trying to get
wait,
it.
It's
see
very
part two.
unusual.
No. Sean had this yesterday on his oscilloscope.
Really? Yeah, I've never
Yes,
seen
he
that
did.
before.
Nice.
So
Yeah. Beautiful.
let me see. Sorry, always the investigator when I look at these things. I want
Please
to know.
pull it apart. Tell me if I'm wrong.
No, that's definitely a Tesla coil ring right there.
Oh, it's a
I
Tesla ring?
figured it was a ring. It's ringing down, so to speak.
Yeah, then you got a high peak, so you got an amplification of the ring.
Yep.
Yeah, that peak is incredible.
There it is. That's your amplification right there. There's
Yep.
your ring. Yeah, Gerald, you might be in that range. That
The next
scalar.
one, I pulse
Does
it.
that mean he can transmit wirelessly?
Oh yeah. I
Yeah.
shouldn't say that,
What?
but
It's like I told Gerald before, he probably has built a Tesla coil into his coil and didn't know it.
Mm.
It makes all the sense in the world with what he's got going on.
Yeah, it's cool. I like that. I don't know. It's you can see what's going on with the wave and the signal and all that. And I really need to get an oscilloscope.
and that's only a square wave pulse. Wait until you see the next video. It's a sine wave pulse.
Mhm.
It's much different.
Yeah, because I need to see what's going on with my coil, and that's really important. I think I might get Pretty Scope though. Pretty Scope. It's an
Yeah, the
it's
one
an
I
app.
have is I got help from a friend to get it, and I only had so much money. I had to get as much measuring equipment as I could to prove that this works, right? And I got everything I could, and that oscilloscope was the cheapest thing I could find, so I grabbed that. I need to get something real soon.
Mm.
I was going to say, Ben, about oscilloscopes. I mean, my oscilloscope that I've got is a cheap oscilloscope, but if you go on the websites overseas, you can get like a digital oscilloscope multimeter, which is true RMS for £13 sterling. So it's maybe $30, $30 US, and it looks like a digital multimeter, but that screen here will give you the waves, and it's really, really cheap. I don't know if I'm allowed to share the website with the photos, but we can talk outside the room. But it's got a screen like this, and you can connect it to your electric system, and you can see the wave shape, and so you got like it will show up to 10 megahertz, and it's for $30 US. It's just a starting point, because like oscilloscopes are not cheap, as we know. And like the cheapest one I got was maybe $150 or something like that. But if you want to spend a little less and just to start looking at the waves, then you can have a look. They're called Professional Digital Oscilloscope Multimeter True RMS, count sampling rate 10 megahertz, and it looks like a multimeter. And you just hook it up. Like, do you remember John Bedini had a more advanced version of it, but he had a little one standing on the table, and then he could see.
Yeah.
It's like a portable one, and you just plug it on the table, hook it up, and you can see the signal.
I think I've seen something like that on Amazon, but not that cheap. So yeah, no, definitely I'll look into that because that's a good price range for me.
That was a $90 something mini. I tried to grab it and I missed it by that much. I got this cheap thing. So, because I know exactly what you're talking about. He could tap it right into his computer and he had full control. So, I'd love to talk to you about the link for that after, like off screen, so to speak. So, I want one.
Yeah. In fact, I just bought one because I found this is so much fun because you know your digital oscilloscope is usually really big and you have different areas where you do your testings and you just want to see the signal. And so that little portable one, it's so much fun. You just grab it, put it in your pocket, go wherever you want to go, plug it in, and you can see your signal and you can see what's going on. So
nice. Nathan, did you
give me 1 second? I'm working on the picture for you right now. I just want you to see it.
Okay. Yeah, this is what Sean showed yesterday. Is that what you're showing?
I'm gonna show them next to each other.
Oh, nice. Okay.
Oh, I also have an update for you guys on my Rodin coil as well.
Go for it, Ben. I'll shut up.
Hold on, Ben, real quick.
No, you're good.
There it is.
Wow.
Yeah, wow.
That could be identical almost.
I told you I saw it before. I don't miss things like that.
That's
I look
Good
at
eye.
So
Good eye.
that's out of a Tesla coil, Sean's is, and yours is out of your coil. I told you.
Yep. And that's my secondary. That's directly off my secondary with the load.
It's just how you build it and how you got resonance in it. And I knew it as soon as you told me that you put the same signal in both and they changed.
Yeah.
And as soon as they had that change in that drop, I knew what you did. I've been doing this too long.
Yep. Good.
So there you go. That's your answer, Gerald. I gave it right to you.
Nice.
You definitely have it in there.
Nice. I'm glad I hooked up that little scope.
Yeah.
Yeah.
Well, we knew it before. We knew it before you did. Well, I did.
Yeah, I know. Well, we talked about it too, right?
Yeah.
For sure.
I guess the old man knows a couple things, huh?
Old man Bill. Hey, old man builds. When he fries it, he finds out. So
that's right.
I love that. I'm gonna make a shirt. Or
yeah,
if Ben, if you don't make your lab coat, I said it in the comment section before. You can pick up on it.
Oh.
If you don't make the lab coats, I'm gonna order lab coats for all of us. I'm gonna put that symbol on it, and then I'm gonna put like different sayings. When you open it up, there'll be a saying. It'll be Old Man Bill says, fry it and find out. And then on this side will be Ben will have some kind of quote, right? And you won't see them until you open the jacket. So I'm telling you.
I love that idea.
I gotta get me a jacket like that.
It's gonna be part of my merch line. Speaking of which, this is close to the prototype. I'm almost finished.
That's so cool. It's like
hold on. You doing some Back to the Future action over there?
Yeah, well, I want to do some merch.
Wild West.
That's a little different than what most people are used to, right?
Yeah,
so this one's kind of neat. It doesn't fit my fat head, or I put it on for you guys.
Oh, come on now.
See, because this isn't mine. See what I mean?
Oh, that's perfect. No. Say top of the morning to you now.
Top of the morning to you there, laddie.
Oh, that's cool. That is so
dirty
cool.
part your father is to see.
Oh my God, dude.
When your mind is on fire. Yeah, and then it just lights up. Hey, I've got an idea. No. Right?
Oh my God, that's so great.
That's coming, but the one that I'm building, there's wheels on the side here, right? My wheels are going to turn when you turn the lights on. And this big one in the back's going to blink. I've already got the mechanisms running and the circuits built. I'm just putting it onto the hat. So this is not the prototype I'm selling. This is somebody else's work. They did an amazing job.
Absolutely.
But it's kind of like this. So I wanted to show it as a demo as to what is going to be coming out. So there you go.
Oh my god, that was so awesome. I love
Right?
that. We're
That's
gonna be
gonna be
all picked out with our own gear, man. That's awesome.
So I was thinking a hat like that, plus the brain fart jacket. I'm
The lab
sorry, lab coat. Thank you. Like I said, brain fart.
So
So
hold on, we got someone here from Western Australia.
Hey,
Nice.
greetings.
Hello
awesome.
from California.
I actually used to live in Australia for a while, so hi, fellow Australian.
I've always wanted to go to Australia.
Yeah.
Beautiful place. Beautiful place.
Sounds good to
Yeah.
me.
No, and us, Jardo, we go there together. We'll all get punched by a kangaroo.
I bought one.
I would get punched by a wallaby.
Well, we would all create too much mischief. That's
Yeah.
for sure.
Well, there's parts of Australia. Apparently, that's all it's about is mischief. And they have a lot of fun. But doesn't mean it. Yeah, we could probably get in trouble.
Oh, that's so great. Oh, never a dull moment, huh, Michael?
Right. Yeah.
The show always keeps you going.
Yeah.
Yeah. So,
Oh,
did you want to
wow.
show that part too? I really want to show Michael that.
Oh, yeah.
side.
I'm sorry. Go. I will.
No
That's
worries.
my fault.
I have it up too. If you don't find
Just
it
take me
quick.
a second. This one. Oh, hold on. You can't see my screen right now. I'm watching it without everybody else. Give me 1 second.
You're enjoying. You know how many times I've done that?
Video. We're going to show you another waveform. This time we're going to pulse it with a sine wave. All right, check this out. We're at 20 volts per pulse. Sorry, 20 volts per division. I believe that's microseconds, but I could be wrong. 10 microseconds, but we'll change that. All right, we're pulsing at 10,000 hertz, 1% duty cycle sine wave. 3, 2, 1. All right, check this out. This is a sine wave. Remember, 20 volts per division. This is just secondary that you're seeing this on. Look at that. That's at 0.5 milliseconds. That's at 1 millisecond. Look at that. That's a sine wave. Okay, so here's what we're going to do. I'm going to turn up the hertz. Let's see. 20,000 hertz. That's 40,000 hertz. 1 millisecond at 20 volts per division. Look at that waveform. That's a 40,000 hertz sine wave, 1% duty cycle. Isn't that crazy? All right, let's turn it up a little bit more. That's 50,000. I'm not seeing it on the scope. Let's go down. I lost resonance. Let's go back down here. There we go. Wow. You see that, everybody?
Yeah, this one's a little longer.
Oh, it's not that. I'm looking for a waveform. I think you got an H wave in there.
So how do you tell if it's an H wave?
Well, he's got his thing out of focus a little bit.
Mhm.
Yeah.
He needs to focus it in, but you can still see it.
Look at that. 20 volts division. DC 2 millisecond on hold.
I guess I would
Okay.
need to see what a regular signal would look like.
Hold on. Let me see if I can't find it. Yeah, if you ever wonder what I do during the day when I look at all my stuff, this is it.
Nice.
Sometimes you have to.
I can see
Frame by
the
frame.
peaks. You can see the peak and how it's doing it, but I saw a clear one earlier.
Yeah, you and I'll have to go over that one time, and I'll mess around with the settings. Or when I get that handheld scope that Michael was talking about, we'll have to redo this experiment.
I need to get one of those as well.
Yeah, Ben, can I put the link in the private chat?
Sure.
Absolutely.
Yeah.
You can kind of see it here. It looks backwards. You notice how you have the two lines and then the tip?
Oh,
So you can kind of see the H wave where it expands off the top because it's a square wave, and then there's a back of the chair or an H.
right.
Oh, at
There
the
it
top,
is. You
yeah.
can see a little better right there. So you just have it like, I don't want to say it's too wide out. You need to come in some more on your scope so you can catch those. But
Yeah,
it's
I
there.
noticed by that.
It's right there.
I will catch that on.
There you go. Right there. Look on the left-hand side.
So on the left hand side, where exactly? Where it's
Look at every single one of them. You have an H on every single one of them.
I have a question for Gerald.
Oh, I see what you're saying. Yeah, Michael, go ahead.
You know, on that image, there's like a pointy arrow which looks like a cursor near the sine wave. Actually, near the wave, I should say. Is that your zero, and then below that is your negative and your positive? So it's like there's a kind of sine wave.
Yeah.
So we've got a positive and a negative cycle, which is amazing. And then what's fascinating is you have a wave inside a wave.
You caught that, did you?
Yeah. Fascinating images, to be fair, but yeah.
It looks
See
like
that as well.
Yeah, it looks like the wave is going by, and then within the wave, it almost looks like it's flowing.
I love
Even
that.
the next wave in the opposite direction.
Yep. Kind of like the wire we see in the nested coil of the Rodin coil design, the nested design. You know, it's the coil, and then inside it's the one single wire that's kind of going, up and down.
Like a field within a field.
You see it now, Gerald?
Oh.
Yeah. The little that's cool. Yeah, the peaks have little tapers off. They taper off a little bit in the shape of an H a little bit.
Nice.
Yeah.
Yeah, like I said, that scope's not very good, but I'll get a new one. We'll redo this experiment. I have many coils to test on a scope, that's for sure.
It's just interesting because we looked into Bedini, one of the first episodes we did, and he got the same exact spike. And what's ironic is he's also getting the ring, and then you're showing this almost as a coupled resonance. Okay,
Mm-hmm.
so it's like where you hide the sound wave when you go to do your amplifier.
Yeah,
So
kind of.
it's kind of what you're getting. It's
I
interesting.
I see it as like because I'm pulsing my primary and I'm capturing the back EMF. There's a mirrored image, and there's also a reflection that occurs. So when I pulse the primary and it goes into the back EMF, unless I absorb it all instantaneously, and my pickup coils are not set up to do that. I only had one pickup coil in there. What usually happens, I'll get a reflection back into the primary, and then it rings back. So it goes back and forth consistently. There is a way to make it consistently ring, but I have to have a whole setup for that.
So take a look here. This is what Michael was saying. It's now backwards.
Yes.
It's interesting.
You're talking about that flow on the inside?
That H is backwards. Your chair turned around.
Oh, yeah. Okay, I see what you mean.
That's what makes it interesting.
Yep.
You're going to have to get that scope dialed in.
Yeah, because then I can dial in the coil properly and tune it so that it's... Because I have control over my heat. I have control over my excess power. I can put it anywhere in the coil. I can put it anywhere in the pickup coils. But I'm still not quite there yet. So, yeah. I that's why I put it on the scope. I want to start tuning it in properly.
I think if you have you've got this one, this digital portable oscilloscope that you've got. I think if you have the other one, what would be interesting to see is if you put one probe on your secondary and then one probe on your primary, and see if the waves if they
are the same but invert.
Right. So from my setup here, if they are in resonance, the wave is almost mimicking the same one. So in resonance, the wave are almost going together, if you like. But out of resonance, my wave can be 90 degree, 180 degree offset, or they can be completely off. But when they're in resonance for the scalar wave setup, it's almost a perfect match. There's a couple of degrees out of phase, but they're almost in perfect match, and it's really interesting. Yeah.
Nice. I can't wait to get the next scope. I have some experiments to do, and I have many coils to do them on. Especially that big coil, the 2-footer. I want to test that.
So like this one here. I sent a link to Ben the other day from German people who did a replication of this PoE coil, and the coil is enormous. This is it's next level coil.
Nice.
The guy turned it on, and within seconds they've got ozone coming out of it. It's like, okay, let's have a look at it. Okay, let's turn it off.
Yeah, it's too much energy.
There's so much ozone coming out of it. Like, oh yeah, let's turn it off.
Yeah, because if it's outputting ozone, that's gonna be a lot.
I've never seen like a PoE coil so. It's just a small dog. It's absolutely enormous. Like this thing. Imagine they probably need like 100 feet of wire. I don't know to do this thing.
For something that size, my coil's 750 feet both ways. So I don't know what a Rodin coil puts into something that size, and the PoE coil, that's an interesting setup. So yeah, I don't know. That's interesting. Yeah,
I always imagine what would happen if you built like the world's biggest Rodin coil, like really like thick industrial sized gauge wire.
0 gauge copper from like battery cables. That would be interesting.
How would you wind it though? It would be so big.
I already know how to wind something that big, but I'm not gonna tell anyone.
Yeah, no, I wouldn't say anything about
Till you see it,
that.
I'm not going because you wouldn't believe it. You just wouldn't.
Hey,
But when
Gerald,
you see it,
that piezoelectric disc and that ultrasound machine.
Yeah.
You see this waveform right here? You see what it's doing to it?
oh yeah.
That's when the buttons push. So we have to talk about how to get you the ultrasound thing with the piezo buzzer.
Oh yeah, because I know what you're talking about. Now that you're seeing the waveform, it's just a matter of tuning it to the point where I hit it and it goes.
Yeah.
I know exactly what you're saying. I don't need a buzzer. I have well, maybe I need a buzzer.
It's the ultrasound box that you need too. It's kind of a unique setup.
Well, what I've been doing is I've been pulsing. I got a piezoelectric, I think it's like a 5-watt speaker, and I've been pulsing that. And I haven't looked at the waveforms, but it's been doing some interesting things, if you know what I mean. And I use the it's like a plasma igniter for propane barbecue, and it's a real decent one, and it gets just a purple spark. And it's about an inch long. So I've been pulsing the coil with that. I'm getting some interesting results. Stuff we'll talk about soon, probably Wednesday.
Mine blew out my hearing aid in my ear when I was testing. I was too close to the ultrasound machine part, and it just blew it completely.
See it, and that's the thing. So maybe I do need, like you said, that buzzer and that specific circuit to see if it. Yeah.
If you were to try, I'd like to try yours as well, though. Anything that sparks over works for me.
Yeah, for sure. I understand that.
Do you have to buy hearing aids in bulk with how much you get through?
Honestly, they normally in the house is where I leave them, and I won't take them out here because
Okay, yeah, that's smart.
I can't hear bass sounds, but I can hear the other sounds like treble way high. Like it hurts my ears. So that's why I never bring them out here, because usually I get those like sirens and stuff like that. But
yeah, it'll just go crazy.
Little thudding sounds, you know what I mean? I can't hear.
Wow.
What do you think, Michael? We got some strange stuff going on here, huh?
Yeah, really cool stuff. Yeah, really cool. I'm looking forward to Gerald's little talk, maybe in the future. So yeah, really interesting.
Yeah, I'll let a lot more out. I'll let out my theory, which seems like a combination of a lot of different theories, because like I said, I joined the scientific community about 3 years ago, 3.5, and just trying to put together what it is I'm seeing with all these different anomalies, because they've accumulated to the point where, like I said, I had to write a book. It's pretty much done. I just have to get it proofread, edited, call it what you will. But yeah, trying to find the theory that fits was very difficult, because there's so many different aspects of these coil systems. Geometrical forms are the key. And like Nathan had brought up, Mandela's from hundreds, thousands of years ago, they knew what we're talking about. I don't know if they had electricity as much as they had electrostatics, and they knew how to manipulate it. So that's kind of where my head's at with this. This stuff's ancient. We're not the first ones to do it. We probably won't be the last. But like I said, let's make a darn big splash while we're doing it, because it's interesting tech that everybody should have their hands on. I see in the future a system that goes into every house and they take care of their own electricity. Could you buy from your local? For sure. We don't want to stop that. But your lights, your heating that you can use through induction heaters in this tech, and maybe even heating hot water. We'll get into that in the future.
Especially, yeah, because the grid goes down with weather, bad weather. You know,
But you still
an
need
emergency. Yeah.
But I'm not talking negating the grid. You still need the grid, right? These systems
Right.
are great, but as far as 220 goes for your stove or your dryer or certain things that are really high powered, I'm not sure if we're quite there yet. But to implement these systems into your house to negate, say, half of that, I see that in the future very easily.
I
We
think that's
take a load off the grid too, you know.
Yeah.
I think that's a good point, Gerald. I think the idea is not to create conflicts of interests. So we don't want to upset any businesses that are providing oil or gas or electricity. But maybe we could have like small little battery chargers that could help us when there's blackout or there's things like that.
Yeah.
People in remote places actually freeze to death. So those are serious topics, and obviously, you know, we want to make sure we play by the rules and that the people in high places are happy.
Yeah,
Right.
yeah, exactly.
But yeah, I
Yes.
get what you're saying, though. Yeah, play by the rules by far. Yeah, I don't want to step on anybody's let's just say, you know, old balls. I was thinking about the shirt. I'm sorry. I don't want to step on anything. It's just a matter of if we can implement sort of a half and half, right, where everybody can take care of their own electricity in emergencies and take care of their lights for free, a little bit of heating, you know, pay the electrical companies for heating your hot water and your hot tanks, your hot water tanks, and your stove and dryer. Everybody gets a piece. There's more than enough going around. We all know there's more than enough people in the world that can use it, right?
I don't have to pay an arm and a leg to build a little mini jacuzzi for my dog. You know?
And you know what, it will happen, and the reason why it will happen is because the population is growing. So what's happening is it's putting more pressure on the energy companies. So eventually they'll reach a point where energy companies will need to find easier sources of electricity, and it puts less pressure on the nuclear powers, on the whole system. So there'll be something that'll come and offset the whole thing, and they'll probably still be in control, still be in charge, but it will be cleaner energy. It will be healthier energy. You know, like this thunderstorm engine or whatever. Like cleaner system.
Thunderstorm generator, yeah.
Like, you know, using water perhaps to run the cars. Perhaps, maybe, we don't know if it's going to happen, but just cleaner technologies would be better for the environment, the people, our families, our loved ones.
Well,
not everybody has to have them, but if a good portion of people have them, it makes a difference, you know.
I'll give everybody a little nugget. The thunderstorm generator is awesome, but it's based on a work by a man by the name of Paul Pantone. He came up with it first years ago. They declared him crazy. They locked him up. They put him in prison for all kinds of things that were proven to be untrue after. And he took his tech and he went to Mexico and opened a university teaching how to build this tech and teaching people that could teach others how to build the tech. Then the thunderstorm generator came out, I believe, last year or the year before, and it's the same tech. It just, the only difference is rather than having a reactor within the motor, he took the reactor and put it outside the motor. It's the same principle, it's the same interactions, everything. And Paul Pantone used to run his system on water, coffee, Coca-Cola, Pepsi, urine, you name it, it would run on it. It didn't matter what it was because of the way that the plasma reactor burned everything 99% clean. So when I hear about the thunderstorm generator, hey, I applaud Malcolm Bendall, but I like giving credit where credit's due, and his tech is Paul Pantone's tech. He just put a spin on it. That's my opinion. If I'm wrong, I apologize, but yeah, so there's a little nugget for you guys. Dig for it, you'll find it. I got a lot of Paul Pantone stuff. I have all of his designs because he gave it out for free. I'll dig it up for you, Nathan, and I'll send it to you. And it shows that this tech was already made. So, I mean, hey, don't get me wrong. What Malcolm Bendall's doing on, I think he's got it on a ship, and he's got it actually powering part of a city. Hey, man, I applaud the guy. He's brought it to a commercial level. That's something Paul Pantone didn't do, and he should get kudos for that. Yeah. But Paul Pantone should be mentioned. That's just my thoughts.
No, you're right. Credit where credit's due, and we're all building off of the footsteps of giants.
Yeah, at least mentioned. Like I mean,
or the shoulders of giants. Why did I say footsteps?
The foots of giants. I like that one better. But you're right. We're definitely standing on the shoulders of giants. Without the inventors that came before us, where would we know where to look or how to even experiment? Yeah.
Hey, real quick, Michael, will you show your coil? Somebody in the chat, I don't think they were here in the beginning. So,
so
there's
that
the
coil candy,
10-inch by 5-inch, and we've got 24 wires at the start, and then this is the 24 wires in the finish. And then I'm still you can see the ends are black. I've just burned the enamel, but I need to sand it down and connect channel A with channel B. And then I've got, this is more like a test really, this is a bifilar wire inside the torus, wound right here inside the actual frame. And I've got 3 turn counterclockwise and then 3 turn clockwise. And I just want to see if I can actually pick up any power from this 90-degree coil. But still trying to respect the proportions and the wiring and the twisting that Daniel and Erica Nunez shared kindly with all of us. But this is just a little twist just to experiment. And I mean, this is just an experimentation device just to learn and understand. But yeah, it's really, really pretty. So it's got 11 rings. Each rings has 14 grooves. I did 14 because I could. I was trying to fit as much as I could in there, so I did 14 grooves. And I think for my next design, I'd like to remove 2 inside. I'd like to remove 2 teeth or spokes. I call this a spoke. So I'd like to remove 2 spokes from the inside, and the reason being is my wire, I don't know if you can see, but inside is really twisted quite a lot. And I want the wire to actually flow nicely, just have this nice bended shape, but it's not like here it's like, it's sort of forced inside, if you like, right inside there. Yeah, it's sharp turns, right? So you're kind of trying to twist into place. And I have seen on some of the design of Daniel and Erica where 2 spokes inside actually are removed.
Are missing, yeah.
Yeah, missing. So there's a nicer flow, because inside the twisting of this wire is a bit too sharp. On the outside, it works really well, but on the inside it's a bit too sharp. So I have seen some design where they have the spokes inside, and some designs where they have removed 2 spokes inside. It's probably a bit more difficult to wind it without the 2 spokes, because you have always to think in your mind, okay, so I'll go 1 step to the right and then 1 step up, right? But you don't have this, you have the spoke missing, so you have to imagine in your head where it should be and make sure you don't miss a step on the other side. So it's a little bit more difficult, I think, without the spokes inside. But yeah, it's big, but I have seen bigger. And there's a small one that I did. This one has a lot of spokes on this one.
That's a nice one. That's
yeah, you
really
can see that it's really tight, right? It's really, really tight. Yeah, so I think this one had And you can see this one. This one I've got. I did it so there was one groove missing really, and it flows nicer. This one, but so
it looks nice.
Yeah, this one's really fun. And this one I found it easier to wind. This one, the big one, I found it easier. So I guess the for people starting with this, try to do a big one. I think I used maybe I would say probably I would say I had I had 30 meters, right? So I had 60 feet. So looking at this, I've got about maybe 5 meters left. So probably 25 meters, which is about 50 feet. But I guess like Ben, you learned it the hard way, where you were 1 foot too short, and I don't think I could cope with that.
Well, it's a learning experience for sure. But you know, when just a warning to some people who are twisting their multifiler, you know, it does shorten it when you twist it. So you need to account for that. And that's something that I didn't account for the first time that I wound a big one.
Yeah, and once you hit that mistake, you can't go back.
But I do have extra wire now. Yeah, I do have extra wire now, and I respooled it, and it's ready to go for another coil frame. So, you know, it's not a total loss, but it is, you know, it did set me back a little bit. I do have a couple of cool announcements with my research if you guys are interested.
Go for it.
So we are trying, as you guys know, we're trying to roll out phase 2 testing of the Rodin coil system that I have. We want to move it towards more practical applications and away from the stereo amp receiver, the training wheels, as it were, right? So Nathan and Mike Does suggested that I get a trigger circuit and a PWM and hook it up to the power supply and use that. And oh boy, we got some interesting results. And I have a video to show you and some numbers. So let me play the video and then I'll go over the results. All right, so here's a quick update. We did get the PM, the pulse width modulator, the PWM working, and the trigger circuit hooked up to the power supply. We have the old Mark I Rodin coil using a open circuit Nunez method right here, where we crisscross the leads. And we have a circuit hooked up, and we're going to use the multimeter to see exactly what's going on. Now, this PWM is only putting out 20 kilohertz. So I'm not able to change that at this moment. I don't know how to. So it's stuck at 20 kilohertz. But this is around the range that this coil utilizes the Nunez method. So it might be close. And this is some interesting effects I'm going to show you. We're putting 5 volts and 0.05 amps into the coil. We're going to turn up the pulse width modulator all the way to 100. And as you see, we're pushing it up. It's putting the volts back in. We have brighted lights and the fan is spinning quite nicely. 4.7 volts out of 5 volts, so a slight loss, very slight loss there. And we have 0.09 amps, and we're going to check the amperage. The amps do change when I check it because of the circuit, but you'll see in a second. .79 amps out of 0.84, so that's pretty damn close. Pretty damn close. We are not actually within resonance, but I think we're really close to the range here with 20 kilohertz. So when I did the Nunez method and I was testing for the 10 times output on the voltage side, or for voltage output, I did get in the microvolts. I was monitoring microvolts because the Insignia doesn't put out a lot of power. It puts out very little power, especially at that high frequency. When you're putting high frequency into it, you're going to get very little out unless you have a proper power supply, which I did not. So I had to monitor very low amounts of power, but it did put out 12 microvolts on the input and 120 microvolts on the output at around 2150 hertz. And that's like right outside this range, right? This is 20 kilohertz right now. That's 20,000 hertz. So that's like right on the precipice of the resonance range for the Nunez method open circuit for this coil. And that's it. The numbers suggest that it's getting about 74% efficiency. So it's got about 26% loss. And then I hooked it up to the Fireball, which is a little bigger and obviously going to have a different resonance range. And I got different numbers completely because it's a fixed frequency. I can't change the frequency with that PWM yet. At least I don't know how. So I'm getting 46% loss, and that's only 54% efficient on the big coil. Obviously, because this obviously tells me that it's not within the resonance range. But the Mark 1 obviously is closer to that range, so it's getting a little bit more. And I thought that was interesting because this is exactly what it does with the Insignia receiver, right? It's exactly what it does with the stereo receiver, only on a lower power setting. And I wasn't able to actually do this test for a while, and I've been meaning to, and I finally got these components working with the coil, and this is very important on bringing this coil out into like a more practical application, away from the stereo amp receiver. And I thought that was really awesome, and big shout out to Nathan and Mike Does for recommending those components. And yeah, we're going to be, as soon as I figure out how to change that frequency, I'm sure there's a way to adjust it. I tried hooking up the stereo amp receiver to just the trigger circuit where the PWM was hooked up, and it didn't seem to be doing anything. But if I can adjust it, that's going to be a perfect system right there. I have potentiometers and a bunch of Arduino components. Maybe I can find something that'll like alter the frequency.
You shouldn't need it. That specific circuit that you have, you have to scroll through the buttons, and you can change the duty cycle like Mike Does is bringing up.
Yeah.
Oh, the button, the click button, because all it does is turn it on and off.
I think it's the other one. You got to hold it for 3 seconds before it changes the menu, if I remember correctly. It's been a little while.
Really?
Yep.
Yeah.
Because it does say you change the frequency, but I don't. Oh. So I can change the. Do you think I can go as low as 7 hertz though? I don't think those go.
I believe that one goes as low as 2. I could be wrong though.
Well, let me double check, because we could be looking at a good setup for doing the neodymium spheres and finally getting to synchronize.
Yeah.
Let's see.
Yeah.
Now you got the right stuff and got some power behind it.
Yeah. Oh, you know what? That's another thing that I didn't tell you guys. I hooked up the big coil with the neodymium sphere, and I got it to spin. So,
yeah.
I mean, it works. I just need more power.
You're rocking it now, Ben.
Yeah.
Nice one, Ben.
Very good.
Thank you. Yeah. We're on our way, guys. We're on our way.
So I just wanted to show something, if it's okay, Ben. Do you have something else to show?
No, that's it. That's all I got. Let me remove this. There we go.
Just want to make sure this is what you have over there, Michael.
Yeah, that's the one. That's the one actually I bought because it's a fun little gadget, and you can see it's portable. You can plug it to your system, and you get a view of your wave. So yeah, that's the one.
Nice. Very good.
Yeah, it's really affordable. At least £13 sterling in the UK. So maybe in the US, $30, less than $30. and I can see Gerald putting one portable digital oscilloscope on one, on the primary and the one on the secondary, and actually see what's happening. So that'd be really interesting to see, actually.
This is for Ben. Comment section wants us to give you a clap, Ben. Not great.
Good.
Thank you.
Sorry, Michael, I didn't mean to cut you off. I apologize.
No.
No, that's an
No,
awesome.
that was a really good moment. That was a really significant moment yesterday when I got those two components working, and I saw those results. It was very significant, and because it told me everything I needed to know. If I didn't get those results, if just one of those variables was off and I didn't see those kind of numbers, I might have been discouraged and be like, oh, this doesn't work. Let's start something new. If one thing changed with what I did over the past 6 months, right? If one thing changed, I probably wouldn't have actually gotten the results that I have today. And it was just like a series of fortunate events. Honestly, I feel blessed to be here right now.
Well, we told you a while back that's what you needed, Ben.
You did. You know what? Sometimes I have a short attention span, so you just gotta keep on reminding me.
I usually tell my friends sometimes I'm just like a mule or an ass. I don't know what you call it. I don't listen to anybody, and I'm horrible for it. So I apologize to everyone out there. Sorry for the language.
Okay. We all have our idiosyncrasies.
And Michael, I got a question for you on this kit. It looks like a high voltage probe. Is there one in there?
So that's a really good question, and the answer is most likely no.
Okay.
So that's a really good question. So what I would do is, if you're playing with high voltages, probably above 250 volts, you probably want to put your probe and just put it on top of the device. You don't hook it up. You just put it on top of the device because you're looking at the sine wave. So you're not going to get an accurate voltage measurement, but you'll be able to look at the sine wave. So this is not a high-tech oscilloscope. So the probe, it's a really good question. So don't hook up your probe on a high voltage system because you'll probably blow it up. It's a really cheap one, but really handy to have. So yeah, so
no, it's awesome.
Yeah, I don't think it'll go above 250 volts. To be fair, I think you can. You got the ×1 and ×10. I think you can reduce the. If you want to really see the wave to fit in your screen, you might have to change the probe to ×10. But yeah, good question. Don't hook it up to high voltage; you'll blow it up. So, yeah.
Gotcha. I usually put mine about 10 inches away. You can put it a little closer, but I took a wire to it 10 inches away. And it usually picks up everything on the high voltage. If it's lower voltage, I'll bring it closer.
And to be fair, talking about probes, when I put my oscilloscope probe on top of the pancake coil, it messed up everything because the pancake coil was sucking up the power from the probe. The probe was not even hooked up to the pancake. It was sucking power because my light was super bright. As soon as I moved my probe away from the pancake coil, then the light went back dim. So so the pancake coil just was sucking up power. So I left the probe very far away just to be able to see just like Nathan says, just to be able to see the sine wave or whatever wave is showing, just to see the signal, making sure I'm in resonance. So hooking I had my probe on the primary, and then I had the second one, which is I left it away from the receiver, but just to be able to see the wave. So yeah, good question.
Okay, real quick before we go on to anything else, Gerald, I have to show you this because I can never hear your thing on there, probably because I'm deaf. But let me just show you this. Right there.
Oh.
$15, has a little battery in it, and it'll make you come in just like your microphone is right now.
Really?
So as you're recording, there you go. I use that when I record on a separate camera as well.
All right.
Make sure you turn it off.
You got.
I changed the battery so many times, and it's not rechargeable, so you have to buy a new one.
Can you throw the link in the private chat?
Yep, I can get it for you.
Awesome.
I sorry, just a little housekeeping there. I want to make sure because I want to make sure you hear what Gerald says. It's important.
Yeah, I thought it was coming out right, but I guess not. I'll have to work on that one.
Very cool. Yeah, I like the wired one, by the way. It's got a very long wire, about 10 feet or so. So,
Yep.
yeah, the other ones kind of skip out on you a little bit sometimes, or I'm doing high voltage experiments and they get, you know what I mean? They
Yeah.
get flaky on you. I like the wired ones.
Or if there's a fan in the background, that it picks it up. So, yeah, the wire one would be better, definitely.
Yeah, definitely. Sorry about that, guys.
No worries. So my gold and silver coil is on the block right now. It's half done. I'd
Half
take
done.
a break. Yeah, I could have done it all in one day, but I got called to do some cooking for a woman's retreat, so I had to go out of town and do that for the weekend. So now I'm gonna finish it today, but I had to work on some circuits for Wednesday and take care of something else. So I'll probably finish it up by tomorrow, show it off on Wednesday.
Did you have the circuits already built now, Gerald?
I have one, I would say built, but I still have to finish soldering it. It's twisted together. Right? And I got that part up into camera, and then I'll just finish the soldering and I'll record that. I'll edit it for Wednesday so that you can see the circuit being built kind of in real time. Does that make sense? And I've been playing with some other circuits lately, a photo electric relaxation oscillator and an A-stable multi-vibrator using neons. So, yeah, see, there we go. And I can't show the circuit because it probably looks as messed up as all my other circuits. Maybe I should show it. People get the idea. No, maybe not.
Gerald,
We'll show
just so you know, Michael, Gerald has trouble drawing circuits that don't look like body parts. So
It's horrible. I'm cursed. I'm telling you. It's hilarious.
It's absolutely hilarious. He
And I
goes
don't
over.
need to.
We're on a private chat, right? He's so proud. He's showing this thing. You know what I mean? I created this circuit, and it looks like women's body parts. And I'm going, oh my God, Gerald, what are you trying to show me here?
It's horrible. I'm telling you.
Definitely the
Doesn't
artist
matter
here.
what circuit I draw, it just comes out the wrong way. Every
So
time.
Gerald, you're right.
Well,
I
failed
labeled-
too. It's hilarious.
Gerald, I looked at the manual and you're right. I should be able to output 7 hertz. And
There
there
you
is a
go.
menu. You hold down the button and there should be a menu for the low range of the duty and the high range of the duty, which
Yeah.
I think I should keep the low range 1%, right?
Yep.
And then the high range 100% or 50%?
I'd go 50.
50.
Because the 100%, that's all on all the time. That's a slower waveform,
Mm,
right? So your 1% is super fast, and then your 50 is like in the mid range, right?
Gotcha.
Gauge it like that.
I'll definitely try that tonight and I'll have you guys an update for you guys tomorrow.
Right
Awesome.
on. I think you're going to get a lot of updates real quick, Ben. Now that you have the right circuit.
Yeah.
Yeah, now that I have the right component, now that I have the right system, this is cool.
So-
Now that I get it working, I'll 3D print the housing for it and everything. You know.
You
Right
still
on.
want that stereo circuit shown on Wednesday then, or should I bother?
Yeah.
Oh no,
Yeah.
no, you show that because
Okay.
I'm going to use
Yeah.
it.
There you
Yeah,
go.
no, because this is the stereo circuit I'm still going to be testing with. It is an easy it's an easy setup, right? The thing is it is a little bit more involved to set it up compared to this. Like this is basically plug and play, right?
Yeah.
Whereas the Insignia you got to like plug in the wires a little bit and hook everything up like that, but it's still easy. It's very easy and I recommend the stereo for anybody starting out. Like Michael said, start out with a big coil and use the stereo amp receiver. It's the cheapest and easiest route.
I agree, but get a stereo that has an automatic shutoff system. Otherwise, you'll blow it.
Yeah, that's true.
Yeah.
Yeah, something more modern then.
Yeah, Merkaba wanted that circuit too.
Yeah, I'll
'Cause he
definitely.
uses the stereo receiver as well.
Okay.
Mm.
It's basically a series of resistors and like I said, the MOSFET transistor.
Nice. So you're going to show us how to build a stereo amp circuit.
Something like that, I guess.
Something like that.
I don't know what you would classify this circuit as. I used it in the beginning. Like you, I used the stereo right off the hop, right?
Mhm.
And that's when I started to see weird anomalies. So, but this is the circuit I used right off the beginning.
Nice.
Yeah. So hopefully it helps you all. The resistors got real hot after a while, I tell you. You know, because you're testing something that's not, well, it's out of the realm of normal, I guess.
Yeah.
Say
They don't consider these kinds of effects when they build these components.
Exactly. I was studying. Shout out to Terran Earthling. He had brought up. I think it's called, the guy's called V. Rhoda, and he talks about telluric currents. And I've been studying those lately. You know, Tesla with his Wardenclyffe Tower. I don't know if Rhoda copied his work or if it was creative genius finding it at the exact same time, but it's based in the exact same principle. They tap the telluric currents. And how do they do that? They use a big, huge metal form in the ground that becomes magnetic, and they use the electrostatics of the atmosphere, and they slam them together, creating current, and they pull the energy off. I mean, that's a simplistic way of saying it. There's more to it by far, but yeah, basically they were using telluric currents to amp up their system.
Creating a bounce.
Yeah, think of it like what's that electrostatic generator there with the wheel that you turn? I'm brain farting the name of Wimhurst. So a Wimhurst generator creates just strictly static charge, right? But in the earth, you have all these minerals, and you have certain stone and certain rare earth minerals. We don't see that, but there's a magnetic line that's all the way through our soil in different ways, and some parts are more concentrated than others. And if you tap into that, you're literally tapping into the magnetic form of Earth, so the current itself. And if you were to match that electrostatic with the current flow, like Nathan had just said, and balance it, you're able to pull that energy out, and it doesn't affect the Earth whatsoever. Just like B. Sears says, this is a good comment. There you go.
It's a pump. It's a bounce or a pump, however you want to say it.
Absolutely. Some called it an atmospheric pump. Some call it a telluric pump. I think it's a bit of both. You know,
it's like having a balloon on your desk and you just press the top.
Exactly. See, you see it. It's visual there. I like that. Yeah, just squeeze the bubble down and work. Sorry. I get excited over this stuff.
Just make sure you have that bubble formed before you do it, or else you get nothing. You're out of luck.
You're not wrong. You're not wrong at all.
Oh, probably people are wondering what's going on here. A little bit of advanced tech, man. I don't know if you know this, Michael. I work on the gravity flyer, so I'm dealing with fields all the time. I basically got a big field generating machine. The Tesla field holding in a static field. I make a bubble and I bounce it. That's basically what it is.
Yeah, so, you ever see the movie Up? Eventually his house is just going to go up.
That's the goal.
My kid's speakers are going off in his bedroom when I'm doing experiments in the garage. Yeah, there's definitely some stuff going on in here.
Awesome.
Oh, yeah. I have to pull all the cars out of the driveway when I start doing experiments outside. I have to find a field next to me to get into. Yeah, it gets pretty bad.
Yeah, I don't know if you know what the Wardenclyffe Tower is, Michael. Have you heard of it? It's Tesla's atmospheric energy accumulator for lighting cities and creating anti-gravity for everybody. But it got stopped by Westinghouse. No, Westinghouse worked with them. It got stopped by somebody. Help me out here.
I'm sorry, I wasn't paying attention. Who's doing what?
The
Wardenclyffe?
Thank you. Yeah, wasn't it Morgan and who stopped Wardenclyffe?
It was the guy. It was his buddy. Not his buddy, but the guy that he was in business with.
Yeah, Edison already chucked him to the side. Westinghouse.
Westinghouse.
Thank you, Anthony Williams.
Oh, sorry.
You threw it up.
I read it at the same time.
Sorry.
There you go. Westinghouse.
Yeah. And otherwise, we all would have had free energy a long time ago. JP Morgan, there you go. I beat you on that one, Nathan.
Well, yeah, you did. You know, there's a saying, you can't create one without inherently creating it all. And that's what these things are. You literally are going to create everything when you create one. There's no getting around it. It is just everything that I've seen shows you everything that it does. Now, certain things personify certain other things or make, you know, put a magnifying glass on one, but they all do the same thing. They all are capable of it. You just have to twist it the way you want it.
It's all based on the same principle.
It is.
Yeah. Like I said, from doing this for like the last 15, 16 years, however it is, there's so many different aspects in one coil. Mapping it out has taken me so long. And I kind of wonder, like, are all systems like this? And then watching you work with the gravity flyer and you guys experiment with your Rodin coils. Yeah, every system's like this. It's just some are a little bit more intricate than others. And some just do basic aspects of what a full geometrical system can do, if I'm explaining that correctly.
Yeah.
Like I've got coils that they're made for one specific thing. And then I got coils that'll do two things. You know what I mean? So it just depends on the form you're using and how the energy flows around that form that you've created. Hopefully I explained that right.
Well, one of the things is you have to be able to manipulate any field that you put on there. And that's the hard one. So you can create all the fields in the world. If you don't know how to push the pressure points on it, that's going to be the hard thing. So, but once you figure that out, and then I got to figure it out because I had to do like 3 months worth of field tests on my gravity flyer, just figuring out where fields are, how they work, what amplifies them, you know what I mean, stuff like that. Then it's gonna really help with everybody else's stuff. You know what I mean?
Right. Yeah.
So
I totally agree.
Yeah.
Yeah, I can't wait to the next few stages of what we got going on, everybody, because it's going to be a whole lot of fun. And maybe we're going to project.
Yeah. Oh, we're definitely frying some stuff. We're not getting around that.
I fried something last night.
I found a whole box of small little electrolytic capacitors, and I'm going to see if I can set them off in sequence like a drum beat. We'll see, right? I'm gonna try, but
you know those Arduino jumper cables. So I'm using those for the module that I'm using, and I was testing out the coil, the big coil, and it wasn't really doing much. So I turned it a little too high, up to 10 amps, and it started smoking. And then
so good.
Yeah, and then I had to replace the wire because they didn't work after that.
You're following Nathan's favorite pastime. Fry it and find out.
Yeah, I found out.
I love it.
Just so you know, Michael, I work with high voltage a lot. So doing plasma displays and things like that. You know what I mean? Just
yeah, awesome.
All kind of sparks, 4, 6, 8 inch sparks, stuff like that with voltage multipliers and stuff. So one of my favorite pastimes is to fry things.
Oh, that's awesome. I know when you guys were talking about apple pies, right? Yesterday.
That's right. We got some apples to blow up.
Apples now. I'm gonna have to try and make some apple pie, and this is so funny.
That's so great. Ben's gonna try to float his apple over there while we blow him up.
Oh, the apple coil.
Yeah.
The apple coil. Yeah.
We literally got one.
This is great.
We'll have to include that in our little Star Trek scheme. Yeah. He's got an apple coil on his desk.
Yeah,
absolutely.
Hey, Tell that to Sean. He might make you a Tesla coil that looks like an apple. You know what I mean? And it's sitting in a dish.
That would be
I'd-
so cool. That
I'd
would be
love
so
to have
cool.
the time to attempt that again, man. That's a tough one. Making a sphere out of a coil. Wait, I mean, I know that Sean did it with his Tesla coil, but I'm talking in geometrical form. It's difficult. I don't know if it can be done. I don't know. I want to try, but I have too many projects on the go.
Somebody needs to invent a 3D printer that can help us print these coil winds. Like it just print the winding, you know, and just you feed it the wire.
I figured out a way of using a sewing machine and a robotic arm to make geometrical coils, but I need somebody who's good with robotics to get the coordination factor set up right.
You need a mechanical engineer.
Yeah. I'm that ain't me.
I'm not either.
So yeah,
Oh,
we might get there one day though.
That would be cool.
Buy a machine and just plug in what you want, hit the button, and it winds the coil for you. Oh, that'd be awesome.
You got one machine to print the frame, another machine to wind it. Yeah. And all in one.
And another machine to rule them all. No,
you know, it'd be pretty trick if you took your like a multicolor machine for 3D printing, and you just tag the color on it, and then you follow the color as you wind it.
Yep.
You know what I mean? Especially on the Rodin coil, it'd make it so much simpler because then you knew which one was the right path because it was all the same color.
I still have all these forms. I've got like 39 forms, I guess you'd say. They're sheet metal that have been cut out with the form, and you just bend the sheet metal up and you wind your coil on it. And each piece of sheet metal has been painted a different color for the different coil or for the different wind. So I don't know if I'm going to give those out because they're not, I don't know. I'd much rather do it with a 3D printer. Like, I like the way that you did yours with the holes, but if there was some way of having pegs formed in there or a setup so that you could just twist in some form of peg to wind it so that it's still a flat form, that's something I'd be really interested in.
So
Like
what do you go ahead?
Like this one. So this one has, I don't know if you can see, hang
Yeah.
on. There's little pegs coming out of the coil. So the coil was printed. Let me see if I can show
Oh yeah, okay.
an angle. So it's two halves, and then inside there's actually a flat layer with pegs coming out. And then you literally friction fit, and you got your little pegs on the outside. So those pegs are part of the actual torus. So
Nice.
Is that what you were saying? Is that what you were?
Kind of think of it more like a bunch of spokes that are faced up around a circle.
Right.
Right? That's kind of more the way, because winding these coils, they're wound flat down, forming the 3 dimensions, not just around a 3 dimension. The whole wire itself forms the toroid by when you do your interweaving wraps, it forms the 3-dimensional system itself. Yeah.
Beautiful.
So it's a little different than what you guys are doing.
Right. I got it. Sorry, I got it the wrong way around, actually. Yeah. Okay. On the flat surface. Yeah. Absolutely brilliant. Yeah.
Yeah. You know what? The compression of on the circumference of the coil when you use zap straps, or there's so many different things you can use. I just use that because it was convenient. But it compresses the field in a certain way where you can form it, right? And if you can see how your fields are formed in your mind, you can actually build coils and systems where you see the field that's formed by the system itself.
So Gerald, I had this, and you didn't like that one. So I had these, there's a little straw with the screw.
Oh yeah.
So you can always make these shorter and put them in just like that. You know what I
That's
mean?
perfect, really.
Well, that's what I did, but they go around the pieces here, these ones. But they may create a different shape than this one would, just in a different diameter, which wouldn't be hard to fix. You know what I mean?
I see what you mean by that. Your circumference of that post matters to your coil.
Yeah.
Right? Yeah.
Okay. There's a difference between how you build it, you know what I mean? And then how you could do it, because the pegs break off easy when you're putting that much tension on there with 20 gauge wire.
Yeah.
That's the problem. So I have a flat one that doesn't have any of these pegs on there, and then I just use the screws.
Well, on my big coils where I have to use a thicker gauge, I got one that's 16. I use these. These are big bolts. And then I've got like a piece of stainless pipe that goes around it.
Well, hold on. You said the diameter matters. And
Yeah,
now you're telling me something bigger.
No. But the coils that we're building, they have to have a smaller diameter. This one was for the 2.5 foot coil.
Oh, okay.
So it's different. Because, when you're pulling on that, man, you need to have tension to hold it until you pull it off your form, have it all strapped together so that it holds its form, because you need that tension. That's what gives you that plasma instability in between the two lines, where the cross section, you have your electrostatic going one way and your magnetic field going the other, and it creates that. You could call it an Evo, you could call it a node. There's many different names, but it's all the same thing, really.
So they have at the hardware store nylon, which is just like a plastic. And they have it in about 1.5 inches to 2 inches that fits directly around a screw, but it's not as thick as the ones I did here. So it's a real thin, it's a slider piece that goes on there. So we could use those. I can buy some of those. They're pretty cheap. A couple bucks for each bag. So yeah, but I'm just trying to get the straw sucked because they went into the screws. So
all right.
Yeah, they're too thin. So I needed something thicker so I can get the tension without getting the screws messing up the wire.
Yeah, that's why in the beginning I used wood with big long carpenter nails, because once it went in, it stayed there.
Yeah.
Right? But the problem was I had all these forms lying around my basement. I had to figure out a way of swapping out in different sizes, and it's crazy. I'm gonna have to actually dip out for a little bit. I'm making supper for the fam. So if you guys don't mind, are you going on for a little while?
I don't know. I know Michael had to take off because it's late there where he's at.
Yeah, so
I don't know what Ben's doing.
Thank you so much for allowing me to come on the show. Thanks, Gerald, for being here. Thanks, Nathan. Thanks, Ben. It's about 1:30 here, so I think I need to hit the pillow now and go to sleep. So thank you so much for allowing me to be here. I'll see you guys later.
Well, thank you for coming on, Michael, and I hope you come back.
Yeah, thank you for your work.
We appreciate it. Good work.
Keep it up by far.
Thank you so much. Bye. Bye.
I didn't mean to end your show for you, Nathan. Sorry, brother.
Okay.
You said what?
Do you have anything else going on there, Ben? Or
no, I was just gonna test out that PWM real quick to see what would happen if I switched it the frequency there.
Let's test it on another day. We went 2 back-to-back days, man. I went.
You guys did 7.5 hours yesterday. Hey, no, did you go longer?
Longer, it was about 9.
9, yeah.
To both of you, man. I couldn't have done it. That was an awesome feed.
Yeah, it was a long stream, but it was awesome. I loved it. We had a lot of fun.
No doubt. Yeah. I have to kind of bail because I'm getting a stink eye. I gotta go finish making supper.
Yeah.
So I got it yesterday, man. I had to come in and cook chicken on the barbecue as soon as I got in the house, too.
There you go. I'm doing glazed ham with honey on it.
Oh, nice.
Here we go. I gotta go, guys. You have a good one, eh? Thank you.
Have a good night, Gerald. I'll see you on Wednesday.
We'll see you Wednesday for sure.
All right, Ben. we'll do some testing here. Maybe you'll pop on Wednesday if it's not too late, and show us that test.
Yeah. I'll run it tonight, and I'll give you guys an update.
That'd be cool. Give you some time to tune it in before we go live with it. You know what I mean?
Yeah, I don't want to be popping no capacitors again on live. That's dangerous.
Yeah. Right on, man. Well, it's pretty cool, man. Hopefully everything goes well, and we got some more guests that are coming in the next few weeks. We should be doing some awesome shows. Michael was totally awesome. I really, really appreciate him coming on. He built the coil yesterday, and then today he sat with us and talked about scalar waves. That was awesome.
Yeah, and he honestly, he said he had to work in the morning, so like, it's late where he is. So he didn't have to do that. That was really nice of him. We really appreciate Michael for showing us all of his cool stuff.
Absolutely. When he starts his YouTube channel, we'll put it on our list in the description so that you guys have it.
Oh, for sure. He's gonna make a good addition to the Fringe think tank.
Absolutely. All right, guys, that's it for me. Thank you very much. Ben, you got something, or else I'm out?
Nope, I'm going too. I gotta go eat.
I'll see you guys on Wednesday when we Gerald and I start building some more circuits. All right, guys, thank you very much and have a great night. Thank you.
Thanks, Nathan. Good night, everybody. Good night, Nathan.